In this discussion video, we will review rational and irrational numbers. So I want to begin by recalling a definition that a rational number is a number that can be written, as a ratio. So notice that the word ratio is actually in the word rational, written as a ratio, and ratio just means as a fraction, something over something, as a ratio or a fraction of integers. So what I mean is I can write it in the form a over b, where the a and b are integers. And one extra condition I need to have is that the denominator of a fraction cannot be 0. So b should not be 0. So let's write some examples. So something like 2 over 5 is rational. It's a fraction. The top and the bottom are both integers, so it's definitely rational. -4 is also rational. It's not a fraction of integers right now, but I can write it as one. This would be, for example, -4 over 1. Or I could also write it as -8 over 2. So there's actually many ways I could write this as a fraction of integers, so that's definitely rational. What about something like -1.5? So this is a decimal, but I can write it as a fraction. This is -3 over 2. So this is a fraction of integers, so that makes it rational. What about 0.333 repeated? Or I could also write this as 0.3 with a line over it to indicate it's repeating. Well, I can also write this as a fraction of integers. This is 1/3. So these are all examples of rational numbers. So one of the key facts about rationals is that in decimal form, so if I write them as decimals, rationals do one of two things. They either terminate. So terminate means their decimals stop somewhere. So for example, if I had something like 7.681 and the decimals just stop there, this is rational. I could write this as a fraction of integers. In fact, this would be 7,681 over 1,000. So either the decimals terminate, or one other thing could happen, kind of like with 0.3333 forever. They could go on forever. But if they do go on forever, they have to repeat. And the example of that, we saw one, was 0.333 repeating forever. Alrighty, so let's talk about next irrational numbers. So let's give a definition first. An irrational number cannot be written as a ratio of integers. In other words, it is not rational. So let's give some examples of these. Alrighty, so one really famous example is pi. Pi is an irrational number. This is approximately equal to 3.1415, so on. It's okay if you don't know all the decimal digits. The most important ones are to know are 3.14. But it goes on forever and it doesn't repeat. Another irrational example is square root of 2. It can actually be proven, even with pi, that this cannot be written as a ratio of integers. This value is approximately equal to 1.4. Another classic example is e. This is the base of what's called the natural logarithm. And as a decimal, this is approximately 2.718. It also goes on forever, but it doesn't repeat. So pi doesn't repeat and e doesn't repeat. This one doesn't repeat. This one also doesn't repeat. Let's do one more. Let's do cube root of 10. Cube root of 10 is also an irrational number. One of the really quick ways to get examples, aside from pi and e, is to use roots, like root 2 or cube root of 10, because it turns out that any non-perfect root is going to be irrational. So what do I mean by that exactly? So both square root of 2 and cube root of 10 are what are called non-perfect. So let me give you an example of a perfect root to show you how it's different from these. So if I had cube root of 8, that is a perfect root because it perfectly just equals 2. And 2 is rational. So anything, any root that just doesn't simplify perfectly to a nice value like this will end up being irrational. All right, so the key fact about irrationals is in decimal form, we've hinted to it already, but in decimal form, irrationals, they go on forever. They go on forever and they don't repeat. I know that for square root of 2, I only wrote down one of the decimal places, but that's why I put approximately equal to. It's approximately equal to 1.4, but it does go on at infinite number of decimal places and it doesn't repeat. Alrighty, so let's try a practice problem. This is question number 3, parts A and B, which says to give an example of a number between 2.5 and 2.6, that is, part A wants a rational number, and then part B will want an irrational number. So I want you to first pause the video for a minute to try to come up with a rational example. 4, 3, 2, 1. Pause it for a minute and try the rational example. Alrighty, so hopefully you did that. Hopefully you paused it for a minute to try that. Let's talk about it together now. So for a rational one, there are many examples that we can write down quickly. So for example, I could do something like 2.541. I just need something between 2.5 and 2.6. It's fine to put it in decimal form. As long as it terminates, that is going to be rational. Another example is maybe let's do 2.59. That's in between those two, and it terminates, so that means it is going to be rational. All right, part B asks for an irrational example. This one's a bit tougher, so I want you to pause it for 3 minutes to try. 4, 3, 2, 1. Pause it for 3 minutes to try this one. Alrighty, so hopefully you paused it and tried it for about 3 minutes. Let's talk about it together. So I want to begin by giving you a hint. And the hint is to start with an irrational that you know in decimal form approximately. In decimal form approximately. And it's helpful if you know at least a couple of digits, decimal digits. So maybe pi. So for example, pi is approximately 3.1415. Alrighty. So my idea now is going to be to do something to pi so that we get a new number that's between 2.5 and 2.6. So I know that may be a little bit open-ended, but I want you to think about that. I'm going to ask you to pause it one more time for 1 minute to think about this. 4, 3, 2, 1. Pause it and try that for a minute. Alrighty, now let's talk about it together. So I'm going to give another hint. So the other hint is, well, what do I mean by do something to it? If I took pi and I added something to it, like 5, well, that's going to give me 5 plus 3.1415 something something. That is approximately 8.1415. If I were think about this, exactly. It will go on forever. This goes on forever, just like pi does, because I only just changed the first number, first digit, 3 to an 8. Goes on forever, and it doesn't repeat. It still isn't going to repeat. So this means that this is still irrational. And that's great for us. It's still irrational, and we know, how its decimal digits end. So adding 5 didn't quite work because it didn't give us a number that was in the range that we wanted. We wanted something between, what was it, 2.5 and 2.6. So this was a little bit too big. We got 8.14 something. But I think we have the idea now, so I'm going to leave this for you to finish. Try to finish it from here now. I'm not going to finish it entirely because there's a very similar problem that I'm going to ask you to do on your homework. So I want to leave the rest of this for you to try.